Hi everyone and welcome to this 12th video of BIOB20. In this video we're going to talk about Bayesian statistics. Before we start, let's create a reproducible random example with set seed 1 to 3. We will create one of these problems where one of the random variables is hidden and determines the outcome of another one. Here we say that I is a binomial random variable with size 4 and prob equals to 0.45. But the value of I remains hidden and we won't see it. And we also create a variable j, which is also binomial, with a size equals to 5 and a prob that depends on I, which is I divided by 4. So prob can take 5 possible values between 0 and 1, depending on the value of I. So contrary to I, the value of j is known, so we print it. The value is 2, and we now ask the question, what is the value of I? Or more concretely, what is the probability that I would be equal to 3? This is a typical Bayesian problem. We know the initial probability that I is equal to 3, but after we observe j, this probability has changed, and this is what makes the problem difficult. What we're after is the probability that I is equal to 3, given that j is equal to 2. There are many ways to solve this problem, and the first is to use a replay strategy. So we are going to replay the movie a large number of times, and we're going to store the values of I and j into a matrix. So first we initialize an empty matrix and we fill it with zeros. And we say that it has 5 rows, just like the values of I, and 6 columns, just like the values of j. Then we write the for loop, and we cannot use I and j because they're already taken, so we say for k in 1 to a large number, like 10,000. And in the body of the for loop, we just replay the whole movie 10,000 times. First, we replay the distribution of I, then we replay the distribution of j, and we need to store the values. The matrix will hold the counts of variables I and j, so I store this observation at row I plus 1 and column j plus 1. Remember that I and j can be 0, which is not an index position in R. So I add 1 so that the minimum index is 1. And for the update, I just add 1 to that particular combination of I and j. If we look at the values of the matrix, we see that it has been updated, but the columns and the rows are a little confusing, so I'm going to fix that so that it's easier to analyze. I say that call names of math has to be the numbers between 0 and 5, and row names of math has to be the numbers from 0 to 4. This makes it easier to read off the values of I in the rows and the values of j in the columns. Now to answer the question, what is the probability that I is equal to 3, we have to find the answer in the second column of that matrix. The second column corresponds to j equals 2. The other columns don't matter because they correspond to events that did not happen. Finally, to give the probability that I is equal to 3 given that j is equal to 2, we give the total number of cases that I is equal to 3 in the column j equals 2 divided by the total number of cases in the column j equals 2. The answer is approximately equal to 169 divided by 812 plus 1172 plus 169. This is approximately 7.8%. This, in a sense, is the replay strategy. We're now going to see another method to answer the question. We start by looking at the row sums of the matrix. The numbers that we obtain correspond to the total counts of I equals 0 to I equals 4. but those numbers have to follow a simple binomial distribution because this is the way that I was sampled. We can check that the numbers that we obtain match the expectations. The probabilities are obtained by using dbinom with the parameters that we use to sample I, and we say that we want the probabilities for all the values from 0 to 4. And to get to a number of counts, we're going to multiply by 10,000, which is the number of samples that we took, and we're going to round in order to get integer numbers. The numbers are not exactly identical, but they're quite close to the numbers we obtained with the simulation. We can use this to compute just the values of the column j equals 2. To fill the first row, we start with the probability that I is equal to 0. Then we multiply by 10,000 in order to obtain the number of cases that I was equal to 0. And then we multiply by the fraction of those where j is equal to 2. And of course we get 0 because the last term was equal to 0. And row by row we can fill the other entries of the column j equals 2. For the second row we replace the values where I was equal to 0 by now I is equal to 1. The theoretical value 789 is quite close to the previous value that we sampled, 812. And we can do the same for the row I is equal to 2, and we obtain a number that is again quite close to what we obtained previously, and the row I is equal to 3, where we again obtain a number that is quite close to what we obtained previously. Using these theoretical estimates, we can now compute the probability that I is equal to 3, given that j is equal to 2. As before, this is done by computing the ratio, and the result is approximately 8.3%, which is not too far from the number we obtained by sampling. It's interesting to point out that we can make these calculations a little bit more automatic. With the vector notation, we can obtain all the probabilities that I takes any value from 0 to 4. And if we multiply by 10,000, we obtain the expected counts. And if we do the same with the probability of obtaining j is equal to 2, we can in one single command obtain the expected counts for the whole column. Those numbers are the expected counts of I for j equals 2. So if I pick the value I equals 3 and I divide by the sum of the total counts, I obtain the answer to my question. It's also interesting to realize that this factor 10,000 cancels between the numerator and the denominator. I obtain exactly the same result when I replace the expected counts by the probabilities. So we never needed this factor 10,000, it was there just to facilitate a little bit the reasoning. In summary, we've seen that there are multiple ways to solve these Bayesian problems. One of them is to have the replay strategy, when we resample the variables just like they were produced the first time. And the second approach is more analytical, where we compute the ratio of the probabilities given the observations. That's what I wanted to share with you. Good luck with the quiz, and see you at the lecture.